Peterson Park, located in Story County, Iowa, is part of an invaluable natural area of the state, offering diverse recreational activities for every visitor. This destination features trails for walking and opportunities to sail on the calm and crystal clear waters of Skunk River, providing an immersive and beautiful experience with the park's rich flora and fauna.
As part of improvements to connect its trails, upgrades include constructing a multi-modal steel bridge that crosses the river, which will be passing over a sandbar, home of precious wildflowers and majestic native birds at the place.
Hello, we're the Steel Bridge team from the Faculty of Engineering at Universidad Nacional, Autónoma de México.
As part of this challenge, we designed a 1 to 10 scale model of Goya Bridge, applying structural principles while preserving the natural beauty of Peterson Park. To address this challenge, we designed a bridge featuring a lower position arc and asymmetric armor spanning 15 feet on its shorter side and 18 feet on its longer side. Inspired by the Baltimore and Warren Truss design, this structural system enhances structural efficiency, reducing compressive stresses on different elements.
Our bridge is composed of 50 steel members, carefully balancing weight and resistance to ensure rapid construction. Additionally, we designed articulated connections to eliminate the transmission of bending moments. In total, the bridge features 55 connections and assembled in just 11 minutes using 2 boards and 2 builders.
With only 230 pounds of weight, the bridge is capable of supporting pedestrian and maintenance loads and allows safe clearance for rowers beneath its 7.25-inch height. Talking about the efficiency and problem solving, this design incorporates rigid armors in both lower positioned arches and in cross-bracing distribution, both calculated to transfer the stiffness to the bridge's center.
This approach reduces torsion effects caused by the bridge's asymmetrical geometry, achieving an aggregate deflection of 1.55 inches under the dead load of 2,500 pounds.
The creation of this bridge was carried out in 3 stages: design, manufacturing, and construction, which will now be described.
Our design began with collaborative groups where each member developed and presented structural concepts. These were analyzed iteratively using SAP 2000 and AutoCAD to identify critical stress points. This process aimed to maximize structural rigidity in both vertical and lateral directions. Using this testing methodology, we pursued a stiffer, lighter, and more efficient bridge design.
To ensure safety of our bridge, we ran 2 lab tests.
The first test involved shear stress test on bolts, confirming resistance beyond A325 standards. The second test evaluated tensile stress in steel plates, identifying strength differences between A50 and A36 steel.
These findings led to key adjustments in connections and thicknesses. Subsequently, rigorous welding tests showed a strength beyond the base material, giving us confidence to proceed. After verifying our structural design through rigorous analysis, calculus, and laboratory testing, we proceeded to the manufacturing phase and initiated the development of detailed blueprints.
Precision was paramount during this phase. All bridge components underwent rigorous quality inspections to verify compliance with the dimensions and tolerances specified in our blueprints. To ensure weld strength, we employ electrodes and MIG welding techniques. All components were meticulously cut, ground, and prepared to achieve optimal weld penetration.
Furthermore, custom molds were fabricated to guarantee precise alignment and symmetry, ensuring compliance with design specification. Thanks to teamwork and dedication, the bridge came to life exactly as planned.
Once construction was complete, we advanced to critical load testing phase. By precisely distributing weights to replicate competition requirements, we validated the bridge's performance. The successful test confirmed compliance with design expectations.
During the weeks preceding the competitions, we intensively practiced the assembly process throughout multiple timed rehearsals, progressively reducing assembly times as we gained experience.
The bridge lower arch integrates thrust-style internal diagonals, a design innovation that simplified assembly by eliminating the requirement for 2 workers to simultaneously connect diagonal members to the arch. This streamlined approach reduced labor demands, providing a competitive advantage.
Goyo Bridge represents our technical skill and sheer determination.
As a steel bridge team UNAM, we're proud to engineer solutions that respect nature and meet structural demands.
Always ready to face new challenges with innovation and unity.
México, Pumas, Universidad, Goya, Goya, cachu, cachu, ra, ra, cachu, cachu, ra, ra, Goya, Universidad.